First notebook which we're going to go through is this one, so it ends in spitzer.ipynb, and I have already opened it up here to the right. So I'm just going to click on the folder to slightly enlarge the view. These notebooks all follow a very similar structures to the other notebooks we've seen so far, so I'm going to go through them a lot more quickly and just point out the differences that relate to the mid-infrared. So this should show you what Q3dfit can do with a spitzer spectrum of a nearby galaxy that I believe is star forming. First, we are importing everything. Especially, we are importing here this readcf function, which is used to read in the configuration file that is mid-infrared specific and which I will talk about more later. Then we define again the downloading function, set up the whole structure of where we want to read things in and where to save things. And then we go ahead and download the files. So in my case, I had already downloaded them, so it just skips. First file here is just the spectrum. It is in the shape of a mock cube, so we have technically a cube, but it just has a single spexel with a single spectrum from Spitzer. And then this other file here, which ends in .cf, is the ominous config file. And I'm going to open it up. If we go in this newly created directory here, then yeah, there you see it. We should be able to open it with the editor. This is the file that where the user can specify which components we want to use in the mid-infrared fit. And our philosophy is to use some components that are really physically motivated, like, for example, a template for the power emission, the polycyclic aromatic hydrocarbons. But some of the components might also be more empirical, like black bodies, which can be dust emission, but we don't necessarily want to ascribe any physical meaning to it. We really just want to get the best continuum fit out and use that to extract the features that we really care about, like the lines and the paths. Yeah, so far we've been using these config files to specify which decomposition we want, but they are really fairly clunky and will in the near future be superseded by something not much nicer and easier to deal with, like a GUI or some functions. So I will not go into too much detail explaining them, but just briefly highlight some of the things. And you also don't need to really remember any of this, since they will be superseded sometime soonish. So this first line just tells the code which file to read in and in what wavelength range we are fitting. Then for the rest, this first column is telling the code what kind of components you want. Here you see two different black bodies. And then this template here, which refers to a template of power emission as specified in the second column. Any components of type templates, there the code can scale them up and down. And for example, with the black bodies, the code is also able to adjust the temperature of them. You could also include a power law if you want, but it's commented out now. And then we have the extinction and absorption by ice specified here. So going through the third and fourth column, that is telling you what kind of initial gas we use for the amplitude of this component, and if the code is free to change that or if it's fixed. Here, this is a free component. Then the next column, there the meaning changes depending on which component we're looking at. So let's start here with the extinction and ice absorption. There, this column just tells you, defines a kind of shorthand, which we can then use in the other rows, such as for the black body here, just to tell it that we want to extinguish this black body by this particular extinction curve. And in principle, you could have multiple extinction curves for multiple components if you so desire. We start out with 0 extinction as an initial guess, but this is again a free parameter. We use dust extinction modeled as a uniform stream for now, but we're also going to implement mixed emission. We start out with a 500 Kelvin black body here, but it's again left free to vary. And then for the black bodies, we also decide that they should be affected by ice absorption, which again, we start out with 0 ice absorption as an initial guess, but leave this free to vary. And then we're going to the section where we are setting up just some arguments for the cube, like which kind of units we're working with and reading in the cube. Yeah, we can define a systematic redshift, which is not currently used, but maybe in the future. Then we say where, in what range we want to fit. And then we define which lines we want to fit. Here, as an example, I've picked out 8 lines. And we fit all of these with just a single Gaussian for now. The structure here is the same as in the other notebooks, setting up the initial conditions for the line fitting. And we set some boundaries for the velocity broadening. If we wanted to, we could also apply a convolution with a given spectral resolution, but here we just leave spectra as convolve set to none, so this doesn't really do anything, but we leave this block in here for consistency with the other notebooks. Okay, then some more parameters that we define for the continuum fitting, like we give it the name of the configuration file, for example. And then we set up the same parameters for the plotting, where we want, how we want our plots to appear, as we already did in the other notebooks. And then we end up with our Q3D object. So again, we can save it to rerun later from the terminal if we want to. And then we can go ahead and run Q3df, which does the fitting first. And it spits out a fair amount of information. So here we see the best fit parameters. For example, for our hotter black body, it recovered a temperature of 280 Kelvin rather than 500. And it also reports that there are a fair amount of correlations between the different parameters. So one thing to do would be, for example, to use a full MCMC fitting routine to get a better look of these different degeneracies. But for now, let's plot what we have running the Q3DA routine. And it starts out with zooming in into some of these lines that we have fitted, so we can see a little bit better what's going on around them. Maybe I should hide this so we have a better view. Then here we see a plot of the total spectrum. So the Spitzer spectrum is shown in black and our best fit is overplotted in red. And you can see the residuals below. And then it's also showing you the decomposition into the different components that we defined in the configuration file. So here we see, for example, template 0, these light blue, really spiky features. That is the PAR template that we included. And then we see the two black bodies in violet and orange. And the different lines are also highlighted in red. And the total fit is then shown in this kind of cyan greenish line on top of the black data. Okay, so this was an example of just a 1D Spitzer spectrum where we didn't really have to deal with the PSF effects yet. We also have an example using a MIRI mock cube. It's this one here, ending in mock etc cube.ipynb. So I'm going to open up that. Yeah, this is a mock cube using the the exposure time calculator for MIRI. And only a single band 3, which is a fairly narrow wavelength range, so we don't have to deal too much with the different fringing effects that Andre was showing before. And it starts like the others by importing some routines, including the readcf routine, defining the download function, setting up the structure for bookkeeping, and then downloading the files that we need in this case. So hopefully it should be downloading this soon. It's in a new directory. Yes, okay, it seems to pop up twice, but never mind. We have, again, first just the mock cube, and then the associated configuration file, which we're using here. We are fitting just a single PAR, one black body, and one Gaussian line in this case. And for the PSF component, we are using the central spaxel again, which is then changed in shape by a convolution with an additional polynomial. I'm going to talk about it a little later in the code as well. For now, we are here providing more information about the cube, reading in the config file. And there we can see that this is a 16 by 25 spaxel cube in this narrow wavelength range going from about 11.5 to 13.5 micron. Okay, we can again define systemic redshift and the range to be fitted. And here we are using again the make QSO template routine to go into the central spaxel, which we assume is completely dominated by the QSO, and take that spectrum as a template to be entered into the fitting. So this is the spectrum in question, which is plotted here. And then an additional polynomial is applied on top of it to let the code change its spectral shape to try and account for the wavelength-dependent PSF. We have just a single line in this data cube, which we fit with a single Gaussian. We're not really tying any lines here. We again provide bounds for the line broadening. And here we are convolving with the spectral resolution of channel 3A. Then we are providing a few more arguments for the continuum fitting, mostly again where to save things and which one is the configuration file. Plotting arguments. And this keyword here is telling us that we would like to have a plot that returns the QSO host decomposition recovered by the code. And then we put all of it together in the Q3D object, which we can again save, and then pass to the fitting and plotting routines. So I've chosen here Spaxel number 612. So this is out of 1625, which means it's a Spaxel that is just slightly offset from the center, but not too much. And then we run the fitting first on it. And plot. So this is the best fit that we get out of it. Then here is the host contribution recovered by the procedure, as well as the QSO contribution. And we can see it better in this summary plot, which is showing the mock data in black, overplotted with the best fit in red, and then the QSO host decomposition as recovered in this example is shown in cyan and violet. But here I'd like to put a big disclaimer that this is currently still very much in development. And the real decomposition will be strongly affected by the spatial variation of the PSF. Currently, we have done a purely spectral decomposition, but different strategies to deal with the PSF are on their way. And so I'd just again like to ask you to please not use this for science right now, but we can still have a look at how it will look like in the future.